Okay, we rotated a metal strap on top of a domino on top of the table. The domino in contact with the table. Generally, the rotation was such that the domino rotated on the smooth tabletop, and there wasn't a lot of rotation between the strap and the domino, but sometimes there was. Okay, well, the question was then, is the acceleration uniform? Is the acceleration of that strap uniform through all the trials? Well, first of all, what do we mean by the acceleration of the strap? It's not going anywhere, it's just rotating. Well, we measure the acceleration as angular acceleration. The angle of the strap with a positive x-axis, and we can set up a positive x-axis and a y-axis. Okay, if we measure the angle counterclockwise from the positive x-axis, well, the thing goes through 90, 180, 270, 360 degrees, and then another 360 degrees that's going through 720 degrees, and another 360 is 1080, and another one's 1440. Okay, so in degrees, you can get the angular position. Much more convenient to use radians for reasons that'll become very apparent as we go through the course. So you start at 0, you go through 2 pi radians in 1 revolution. If you start at 0, t equals 0, well, if you start from the positive x-axis, you go through pi over 2 radians, that takes you to the y-axis, positive y-axis. Pi radians from the start is at the negative x-axis, 3 pi over 2 at the negative y, and 2 pi, you're back to the start. And then you go through another cycle, you're at 4 pi, 6 pi, 8 pi, and so forth. Okay, well, theta of t is your angular position, which by default we measure in radians. But for the purposes of what we're doing today, you can measure it in degrees if you prefer. It's a little easier to think in degrees, and you probably want to estimate your angular positions in degrees. Just be careful that, when we get into the real mathematics of this, radians are going to be more useful. Okay, well, theta then is just like position. So what do we mean by angular velocity? Well, just like velocity is the rate of change of position, angular velocity is the rate of change of the angular position, the rate of change of theta with respect to t. So that would be like delta theta over delta t would give you an average angular acceleration, just like delta x over delta t would give you an average acceleration for something that's moving along a line. Now, we don't use v for this, or v bar, because it would be an average, because we don't want to confuse it with something actually going somewhere. So we call it omega bar. We call the angular velocity omega, and this is omega bar, and this defines your average velocity. In the limit, as delta t approaches 0, this becomes instantaneous angular velocity, and that's something that's pretty straightforward because everybody has a pretty good calculus background. Okay, so that's average rate of change of angular position with respect to clock time. We call that angular velocity. And then angular acceleration, well, just the rate of change of angular velocity. So the average angular acceleration is change in angular velocity divided by the change in clock time. Average rate of change of angular velocity with respect to clock time, angular acceleration. Okay? Now this thing is omega, it's not W. For reasons that I explained in class. You don't want divine retribution. If you call this W, you might get it. Okay. And omega is what we call angular velocity, alpha is what we call angular acceleration. And then what we did was we timed the time to rest from, we just gave it a spin, started the clock when we completed the spin. Some people started the clock when they started the spin, which leads to some error, but not a terrible error in this case. And we didn't worry about that too much, although in the future we certainly will. So we recorded our data. Through what angle did we go? Okay, well, here are the angles people had. People went up to about 2.5, actually close to 3 revolutions. And people had as little as, 100 degrees, which is a little over a quarter of a revolution. And of course, the delta t to rest was in counts. We used our 1, 2, 3, 4 count, but we regulated our count with a pendulum. So right here is the length of the pendulum, 27 centimeters here, and how many counts were counted per cycle of the pendulum. So if you were counting 1, 2, 3, 4. That would be 2 counts per cycle because the cycle's from here to here and back. Okay, back to original point and original velocity. So there's the data for that. And from the length of the pendulum, we can easily solve a simple differential equation and figure out what the duration of a cycle is. Of course, we need to use a few vectors in that. We haven't done it yet, but we will very soon. So here we have a definition of our count, assuming count is regular, and people are pretty good about keeping it regular. I don't think that introduces a huge source of error at this level. And then the time to rest, so then people figured out the angular acceleration in degrees per count squared, usually, and the initials of whoever wrote this down and whoever's in the group. So these are the 3 groups. And then we went on to the Atwood, and we wanted to get the acceleration versus the number of clips transferred, and is acceleration uniform within a trial? Those were the 2 questions that we tried to answer with the experiment. And we, I'm getting this up here a little bit late, mainly for the record and for reference later on. People have already submitted their lab reports, and it appears that the results here for the Atwood machine aren't what we would expect. We don't seem to have a linear acceleration with the number of clips transferred, although that's pretty much what has to happen. So I'm going to have to get my hands on this system and figure out why it didn't happen. And then the question, is acceleration uniform within a trial, which is a little tougher. And I expected to get reasonable results here, some reasonable linearity of acceleration, or some reasonable consistency in the acceleration within a single trial. And I'm not sure we got that. So this is really good, it's really entertaining. It tells us that we've got something that we don't understand that seems to be at odds with what the rest of the physical universe has observed over the years. So it's an interesting situation.